Welcome back. Today we will discuss on the ductility detailing for earthquake forces. This is as per the code Indian Standards 13920 and the recent code is published in 2016. So coming to the ductile detailing, the objective is to provide adequate toughness and ductility to resist severe earthquake shocks without the collapse. So this code deals with several detailing practices and some concepts which help the designer to design a building such that it won't collapse at a earthquake load. And the IS code 13920 is called the Code of Practice for Tactile Detailing of Reinforced Concrete Structures Subjected to Seismic Forces. So where this ductile detailing is required. These are mandatory in seismic zone 4 and 5 as per the 1993 code. Also, the structure in seismic zone 3 for a building with importance factor I greater than 1. Structure in seismic zone 3, and if it is an industrial structure, the structure is located in seismic zone 3 and if it is more than 5-story high. The design of structures is as per the Indian Standards 456-2000 and for all the structural buildings, the grade of concrete should be minimum 20 megapascal and the grade of steel should be minimum Fe 450. Generally, there are two types of damages for a beam. One is the flexure failure and the other one is shear failure. So you can see from the figure 1, when a beam is subjected to bending, the top will be under compression and bottom under tension. As concrete is weak in tension, there will be the flexural tensile failures. So the bottom face stretches in tension and develop vertical cracks. Similarly, you can see the shear failure, which is a diagonal failure. While designing the structures or detailing the structures as per the IS 13920, there are some provisions that the factored axial stress under earthquake loading should not exceed 0.1 times the characteristic compressive strength. And also, the preferable width to depth ratio should be more than 0.3. So that means there should be adequate width for the beams. And the minimum width should not be less than 200 mm and the depth should not be greater than 1/4 of the clear span. Regarding the longitudinal reinforcement, at least 2 bar should go throughout the member length at both top and bottom. The tension steel ratio on any face at any section raw minimum is equal to 0.24 into root of FCK by Fy and the maximum steel ratio on any face at any section raw max is 0.025. The positive steel at any joint face should be more than half the negative steel at the faces. So these are the provisions for the longitudinal reinforcement detailing based on the IS 13920. And you can see here The bottom steel at support at least half of the top, and at least two bars should go full length of the beam. You can see beam column here. Another caudal provision is the steel provided at each of top and bottom face of the member at any section along its length should be greater than one-fourth the maximum negative steel provided at the face of either joint. Similarly, the longitudinal reinforcement in the case of external joints for both the top and bottom bars of the beam, anchorage length is equal to LD plus 10 dia minus allowance for 90-degree bend. So you can see here the reinforcement, and LD is the development length in tension. The total length should be equal to LD plus 10 times the dia, deducting the allowance for 90-degree bends. And for the anchorage of beam bars in exterior joints, in the case of narrow column, as we don't have much width for the column, it may be extended into the beam reinforcement should be extended into the column approximately 50 times the bar diameter, and the portion of top beam bar below the socket of the beam. So this is the uh, reinforcement which is inserted into the column below the beam level. And for wide column, we can go for the L-shaped bar end like this. And in the case of ductile detailing, the flexural members, the internal joint that is between the beams passing through the column, we should not provide a crank or bend in the beam reinforcement. Instead of that, reduce the width of the beam so that the beam reinforcement are going inside the column reinforcement. You can see here the beam width is equal to column. If it is happening like that, or if you're providing like that, there is a requirement for bending the beam reinforcement. So it's a poor practice, and go for a reduced width of the beam. Yeah, so this shows the failure which happened due to this poor practice. Shear failure of RC beam column joint during the Mexican earthquake when the beam bars are passed outside the column section. So always the beam section should be less than the column width for the proper steel reinforcement. And regarding the splicing, splicing is all about joining two rebars. In region of splicing of longitudinal bars, hoops to be provided over the entire splice length at a spacing not exceeding 150 mm. The lap length shall not be less than the bar development in tension. Splicing or lapping of longitudinal bars. So you can see here the total overlapping length here. This is the reinforcement 1 and this is the reinforcement 2. We are splicing it to make it into a single action. Splicing or lapping of longitudinal bars. So there are some conditions or restrictions on lapping. The lapping is prohibited in regions where longitudinal bars can yield in tension. So never provide lapping at points of highest bending moments. Supports, midspan, etc. should be avoided. That's the main takeaway regarding the splicing or lapping of the longitudinal bars. In the case of ductile detailing, the lap splices shall not be provided within a joint as there are regions of highest bending moment within a distance of 2d from the joint face. Is from this joint two times the depth of the beam is maybe this zone should not provide any lapping within quarter length of the member where the flexural yielding may generally occur under the effect of earthquake forces. Not more than 50% of the bars shall be spliced at one section. And there are some conditions or restrictions or guidelines for the web reinforcement. It shall consist of vertical hoops, the closed stirrup having 135-degree hook with diameter extension minimum of 75 mm that is embedded in the confined core. So always provide the web reinforcement like this with an extra length which is equal to the 10 times diameter at an angle of 135-degree with the horizontal. This is a 3D image showing the vertical stirrup. The smallest diameter steel bars are made into a closed loop, this green one, and are placed at regular interval along the full length of the beam. The blue is the longitudinal bar, larger diameter steel bars that go through the full length of the beam. Same. So this is actually the hook, 135-degree hooks in adjacent stirrup on alternate sides. The end of stirrups are bent at 135 degree. Such stirrup do not open during strong earthquake shaking. So that's why you're providing a 135-degree hoops. And regarding the horizontal spacing between two ties, should be more than should be designed properly. There is no direct value for that, and the total length should be more than 10 times the diameter of the stirrup. A little bit more detail into the web reinforcement. In compelling circumstances, it may be also be made of two pieces of reinforcement. So if you're not able to provide like this, you can provide it at two adjacent joints or corners. An U strip with having a 135-degree hook and a 10 dia extension or a cross tie. So this is another option, and you can provide like this. The cross tie is the bar having 135-degree hook and a 10 diameter extension, minimum of 75 mm at each end. The hooks shall engage peripheral longitudinal bars. The minimum bar diameter of the hoops for spans less than 5 meters should be 6 mm, and for spans more than 5 meters should be 8 mm. Contribution of bend-up bars and inclined hoops to resist shear shall not be considered. So this shows the reinforcement detailing for the beam column. So you have the column here and the beam spanning between the columns, and all the enough development length, and also the web reinforcements are given as shown in this figure. Minimum two bars are provided for the full length along the top and bottom face, and the regarding hoop spacing should be less than d by 4 and 8 dB. So all those things are detailed in IS 13920 also. So another figure. So the you can see near the column faces the stirrup should be closely located, and at the mid portions we can increase the spacing. The spacing of stirrups as calculated, but not more than d by 4 and 8 times the beam bar diameter. The spacing of stirrups as per calculations, but should not be more than d by 2 at the middle region, and same thing applicable for here near the columns. Regarding the spacing of the hoops, either at either end of the beam, the same thing is repeated here. What are we telling here? Overhead length of 2D, spacing shall not exceed d by 4 and 8 times the diameter of the smallest longitudinal bar. The minimum spacing should be 100 mm and the first loop should not be greater than 50 mm from the joint face. Continuing on either side of the section where flexural yielding may occur, over a length of 2D, spacing shall not exceed d by 4 and 8 times the diameter of the smallest longitudinal bar. Elsewhere, you can provide a spacing greater should not be greater, sorry, not greater than d by 2. Yeah, so that's all for the this video regarding the beam detailing as per the IS 13920.